Okay, so welcome back for our second seminar of this afternoon. So it is really a pleasure for me to introduce the next speaker, who's Professor Sinopoli from Washington University in St. Louis. Now, before speaking about the career of Bruno, let me tell you that sometimes there are people that have superpowers, and Bruno is a person with superpowers, in the sense that since I know him, he is someone who sometimes starts a subject. The subject at the beginning, nobody believes in it. And then 1 or 2 years later, it's always one of the big things in our field. So I've seen it happening for control over networks. I've seen it happening for cyber physical security. I've seen it happen also for other subjects. And so a little request to my researchers in the room: please take note of what Bruno is doing, and let's try to go with the wave, because historically we have a good data set that that's what's going to happen. It's going to be the next big things. So besides that, so Bruno is a very dear friend, was very important for me at the beginning of my career. He has an excellent career. He did his PhD in Berkeley, postdoc in Caltech. Then he was a professor at CMU, at Carnegie Mellon University in Pittsburgh, and now is department chair at Washington University in St. Louis. So he, as said, he is author of several very influential papers, and it's my pleasure to give him the podium so that we can steal from him ideas.
Thank you, Emanuele, for the kind introduction. Thank you all for being here. I also want to thank BrIAS for hosting me here in Brussels. This is a fantastic idea. It's bringing together scholars from all over the world around interesting topics. I think it contributes, I think, to not only to the visibility of the university, but also to science in general. So I'm very happy to be here. And thank you, Manuel, again for the introduction. I'm actually here to learn, so I don't think I have anything new to offer here, right? And to Manuel, I have to say that I think you have learned quite well, right? Your research spans, entomology to batteries. So I think you have your own way of discovering new fields under the lens of systems and system theory. Okay, so today I want to talk about a project which we started about a couple of years ago. And it stemmed from the observation that these days tools such as neural network, deep neural networks, or more generally AI, you hear all the time, right? AI will take care of it. What does it mean? AI will take care of it, as if AI was this deus ex machina who could solve all the problems that you had, right? At the end of the fair, this AI is nothing but a number of techniques or regressions, right, that uses large amounts of data, and very often is an overkill for problems, right? And it substitutes often what we can do through analysis, right? Instead of trying to exploit structure in problems, we just hammer it down with these huge tools in the hope that they will give us the right solution. So, with this mindset, we started looking at problems of dimensionality reduction. Right? Dimensionality reduction has been a problem that's been existing for over a century, right? And that these days completely dominated by nonlinear methods. Okay. And so we wanted to revisit this to see whether actually the current approach is the right way to go, or maybe there is something that we can still recover from or learn from linear methods, right? And whether by adopting linear methods can provide some advantages. Okay. First of all, let me acknowledge so this is, first of all, joint work with my colleague from computer science, Professor Netanel Raviv. And by the way, which reminds me that my postdoc I did at Stanford, not at Caltech. I don't want to create, since this is recorded, it's better to be precise. It's okay. I spent time there, but never. So this is main work was done by our joint PhD student, Baharam Yaguti. Okay, and so this is what I'm trying to. First of all, right. Let me ask about the background. Right, how many people are in engineering here? Okay, not everyone. Okay, and how many people are comfortable with linear algebra? Okay, good. That's all that you need for this. So right. So what we're gonna set the problem of dimensionality reduction. We're gonna very quickly review some of the existing linear reduction methods for, we call it also feature extraction, right, in common data science, right? And then we'll provide an idea or a general approach to solving these problems, which we call iterative redundancy removal, right, which is basically based on Gram-Schmidt methods of orthogonalization. That's all that there is to it. So not only linear algebra, very simple linear algebra. Right? And we show, what I'm going to try to do is convince you that methods of this sort provide a lot of advantages over, the neural network-based methods. And to do so, we'll show in the context first of the usual academic data sets, and also a very specific example which is related to genomic, right? Thanks to the data provided by our colleagues at the medical school at WashU. Right? Okay. So let's set up the problem, right? Problem dimensionality reduction. You have data, right, which are points in RD, let's say, and your goal is somehow to compress this data because you want to do something with it. You want to process it. You want to do some learning. You want to do transmission. Therefore, you will benefit from a smaller representation of such data. Right? And so the usual approach is to project such data to a lower dimensional space. Right? You want this to be fast. Linear is usually fast. And the most important thing is that once you throw away some of this data, you want to preserve the informativeness of this data. You want to throw away data, but not information, right? As my mom always said, you never throw away information. In this talk, we'll look at the problem of unsupervised feature extraction, and also we'll see how the extension to the selection is actually quite simple throughout these methods. Okay, so let's say the data belongs to a subspace of dimension n, which is much lower than d, right? So that there is, in other words, redundancy in this data. And this redundancy is as nonlinear redundancy, right? If the redundancy was linear, we know already what the solution would be. Okay, so it's of this sort. If it's linear, PCA provides the optimal algorithm in order to remove redundancy. So there's a lot of dimensionality reduction methods, right? Of course, everybody knows about PCA. PCA is still used in a widespread manner in sciences. Right? When we talk to our colleagues doing genomics, which is actually a very interesting problem, where you have very little data, very many features, they still use PCA, and there are advantages to it, and I will touch upon it, especially in terms of interpretability of the data. Right, because PCA preserves the global structure of the data, so you do not, and that provides cues as to interpret such data. Locally preserved projections, which preserve local neighborhoods relationship by projecting the data based on the graph structure or the points that are nearby. Independent component analysis, which separates the data into statistically independent components. Then there's kernel PCA, which extends PCA using some kernel trick to capture these nonlinear structures in the high dimensional spaces. And then there are methods which are related to the most recent data science, like UMAP, which are nonlinear techniques that preserve both the local and global structure, and autoencoders, which are just neural networks. Okay. So what is the problem, right? Dimensionality reduction can be applied broadly to two problems. One is feature extractions, right? Feature selection, where basically you choose the dimension or the features as they are, right? You have a number of features and you select some of them, right? While in feature extraction, you compute new features as combination of the existing features, right? Right. And you can provide some information-theoretic guarantees. Conditional entropy, for instance, is small, right? If it's small, basically you are basically preserving the informativeness of the original data by simplifying it, right? And as I said, in this talk, we'll look at no labels, right? And the popular methods which are used today are this kernel PCAs or deep learning methods such as autoencoders, right? And if you go to these conferences like NeurIPS or AI Stats, methods of this sort dominate really to the extent that if you propose linear methods, and I've learned that on my skin, they are disregarded as old stuff, which is irrelevant. That's fine. Okay, so what we want to do is develop methods, linear methods, right? So linear combination of the data, which are able to remove nonlinear redundancies in the data. That is something that PCA cannot do, right? It cannot remove nonlinearities, right? And nonlinear methods can remove nonlinear redundancies, but the methods themselves are nonlinear. And deep learning, of course, can be applied to anything, but you'll agree with me that it has robustness issues, right? There's a lot of data and very poor guarantees or no guarantees are provided. So we wanted to address all these issues, right, by proposing algorithms that identify a non-redundant linear projection of the data. And so in this way, get the best of both worlds, right? And preserve linearity, which provides all sorts of advantages, but remove also nonlinear redundancies, right? And these are some of the goals that we aim to obtain, right? Simplicity, which using the reductionist approach in science is always something that you want to achieve. And we want a systematic approach, not something where you have to fine-tune possibly hundreds of parameters to the particular data that you have, right? And that is deep-rooted in the fundamentals so that we can get some guarantees, right, and a clear direction. Something that is robust and again is low and not very sensitive to the choice of these hyperparameters. Right, and the other thing is provide explainability, which is very important for science, right? And ultimately, right, we want to have a empirical performance which is comparable or better than the existing methods, right? So the general idea is. Right, we have the general idea, which I will explain in a couple of slides, which on one side will provide some practical algorithms that give information-theoretic guarantees, right? And the guarantees that you get are always in the sense of conditional entropy, right? on the other hand, and I will focus much less on this, there are so-called theoretical algorithms. We call it theoretical because it rests on some assumption, which is difficult to validate from the data because you don't have the distribution usually of the data. But these theoretical algorithms can guarantee that if you had, if you were able to verify some assumption of the data, you get exact guarantees. You could guarantee to remove all the redundancies in the data, which is actually pretty cool. Okay, so this is the general idea, right? This is a meta algorithm, right? So let's take the data. Let's say that this is IID from X, and find this informative linear projection, right? So as I said, the hypothesis is that our data set contains redundancy, right? Which is a sum of independent random variable and their function, possibly nonlinear function, right? So the general framework is the following. It's very simple. It's rooted in linear algebra. Project, subtract, and then repeat, right? So an assumption that you'll make is say that the redundancy is captured by a family of functions, right? F in some, these are generic variables, y1 to yd, which is the dimension of the data. Right? We'll see how you don't really need to know precisely the redundancy, right? But if you pick a rich enough functional space, right, then this actually will work quite well. And so, according to some methods, which will depend upon the specific algorithm that you'll pick, you'll find some direction at iteration j, vj, which is some variance maximizer of some distribution, right? And you define a new variable, which is zj, which is generated out of this product, is a new random variable, right? And then what you do, you do subtraction. So you orthogonalize this family function where you keep all the functions up to variable yj, right? And you substitute the z to the yj, right? So you take this family of function, right, and in such that depends only on the first j variables, right, to get an orthogonal set, OJ. And then you subtract this OJ from the data to create a new random variable, right, which you call dj plus 1 of x, right, which is just a projection, right. And then you repeat this routine, right, from j that goes 1, right. Potentially, you could go up to d, but that would kind of defeat the purpose of dimensionality reduction, until you meet some condition, right? That usually it's some variance threshold, right? Basically, you're saying I keep orthogonalizing until there's very little information left in the residual data, and I'm happy to give it away, right? Right. So this is the general idea of iterative redundance removal. So and so let's look at the algorithm, at the different pieces more in detail, right? The tool one is what we call Gram-Schmidt orthogonalization, right? Which is this routine. Right. So basically, you find this variable one by one at each iteration, right? And basically, you orthogonalize f, which is our functional subspace, variable by variable. Okay, where fj, as I said, is a subset of f, which depends. Which contains all the variables which depend only on the first j variables. Okay, and then you call this orthogonalization routine, which basically appends the new functions, which are the functions that depend on the jth variable. Okay, And for all the g's that belong to fj but not to fj minus 1, so these are the variables that contain the jth variable, then you add the following function to the orthogonalized base, right? Right, you can see this as simple vectors, and this does not change. Of course, you have to compute expectations, and you don't have the distribution, so you can just substitute with empirical means. Okay. The second is, how do you choose this direction, right? In order to define the new variables, right? Intuitively, you do in such a way that this variable represents what remains in the data after you have removed the span of the OJ, right? Whatever is left, right? And you can define this alternative covariance matrices, which is nothing but the covariance matrix of the new variable, of the variable dj that you just created, right? And this can be computed inside the orthogonalized routine, right? And so you choose this new direction according to this covariance matrix, right? And then then it's complete. You have everything in order to continue. Okay, so let me connect this to PCA, and hopefully this will shed a little bit of light on why we're doing this, right? So PCA project the data on the large eigenvectors of the covariance matrix, right? So that's what it does, right? The kth component can be found by subtracting the first k minus 1 principal components from K, right? And in fact, if you choose your family function in our approach to be the singleton, right? So you remove all the nonlinear functions from this. Basically, you can say that our algorithm generalizes, specifies to PCA. So in other words, what we propose is a generalization of PCA, where in this family function, we include all sorts of combinations, nonlinear combination or functions of the singletons, right? Which could be polynomials. This depends upon your choice, right? Especially if you have some prior on the data. Okay. So this is the general approach, right? Now let me give you an idea of some of the algorithms that we use, right? And the first one is we call Gram-Schmidt functional reduction, for a lack of a better name, right? So it's an implementation of the general idea of iterative redundancy removal without any assumption on the data. So you get data, you don't know how this data was generated, right? All you have to assume, which is kind of, I think it's a fair assumption, some constraint on the energy of these functions, right? Which is fine, I think, right? So this is how the algorithm works, right? You take this data, IID again from an unknown x, and you define a threshold. The threshold is your stopping criterion, right? How much information you can afford to leave or to lose in this process. Okay, and the output is all the extracted directions, right? Up to m. M, of course, varies depending on m is a function of epsilon, right? The smaller the epsilon, the larger the m, right? Because you want to refine more and more the data, right? So you initialize your first covariance matrix as being the covariance of the data that you have, and of course your subspace is the empty one, right? And then you run the routine from J1. I mean, you could put a while loop. It doesn't matter. Up to D. You take Vj, and this is what specifies Gram-Schmidt functional reduction to be the largest unit norm eigenvector of this covariance matrix. Okay. Now, if this condition is satisfied, right, then you have basically met your threshold, right? And you end the algorithm. Right? If not, then you define the new variables, as I said before, and you run your orthogonalization routine, right? Which will give you the new subspace and the new vector. And based on the new vector, you get the new covariance matrices that then you will use in order to define the new vector. You just iterate. I'm going to leave it there for a second. It turns out this provides some information-theoretic guarantees. So if you take x and epsilon to be the inputs to the algorithm and the vectors to be the outputs, then you assume also that your z to be the new variables that you use in order to instantiate the functions in this functional space. You assume also that you have a finite alphabet, which I think is fine, right? So we have a theorem that says that the conditional entropy is bounded by this quantity, where d again is the dimension of your data points, right? And in order to prove this, it's just a bunch of bounding that you do, right? By the conditional entropy, you can bound it by z orthogonal. And which ultimately you bound by the sum from J M1 to D of H of the entropy of Zj. So all the variables from M to D, the one that you're not using. And so also orthogonalization we know increases entropy. So you can bound this H of Zj with H of Z tilde J, which is just the orthogonal of Zj, and then you can bound again this quantity by epsilon squared, which basically gives you the result. Okay. So that's a guarantee that you get. Okay, but now enough of theory of linear algebra. So let's see how this performs, right? And of course, this is a dimensionality reduction, so you have to instantiate into some problem to be able to characterize the solution, right? And so we apply to classification problem, right? And so you want to compare on the basis of classification accuracy, right? So as you said, remember one of the goals was having a performance which is comparable to existing methods, right? And then with regards only to PCA, see what residual variance is left in the data, right? And here the goal would be to have the same residual variance with less features, right? And which would say that, given that we start with a different family function, we can achieve the same informativeness of PCA, which much less, with many less features. Okay, right, which is basically what I said. Okay, right. So these are comparisons with this coil data set, Columbia. I forgot what it means. Anyway, it's one of the standard data sets that you find, right? And here we are comparing the classification accuracy of support vector machines with where we choose a radial basis function kernel. Okay, and we are comparing GFR, which is the method that I just described, with linear methods. That's an apple-to-apple comparison, and also with kernel PCA, which is apple to oranges because kernel PCA is nonlinear, right? Where we use the same functional space. And here are the results. So our method is in blue, and as you can see, it consistently outperforms all of the other existing methods, including kernel PCA, right? And the gap is well, I don't know that I can say, right? Where on the x-axis, there are different performances as a function of the extracted features. Okay. And you can see that the gaps become wider as we choose less features. Okay, which. Okay. And we have performed other examples with USPS datasets, only to get very similar results. So this is actually a comparison with autoencoders, neural networks, and UMAP, right? Which are the state of the art if you talk to whoever is anybody in data science. And this is very interesting because I think it speaks to one of the other properties of our algorithm, right? First of all, here this is our accuracy, GFR, and this is the accuracy of UMAP, and with respect to two data sets, NIST and again the COIL 20. And on the bottom, you'll see the comparison with under the same data sets with autoencoders, right? And what you will see, first of all, right, the results that we get do not depend upon any parameterization, right? So you don't have to fine-tune any parameters. It's very fundamental and very systematic, right? Whichever the data, you apply the same algorithm, right? Which is something that you cannot afford to do when you use these methods, right? As a matter of fact, this variability this is some quartile or some, which I don't know, which I actually don't remember what it is. But this is the average performance, but you will notice that, and this is the variation that you get depending on the choice of hyperparameters. But what is interesting to notice is even with the best choice of hyperparameters, which is something not to be taken for granted, we do better than UMAP, than these nonlinear methods. Was this enough to convince the NeurIPS community that this was a worthy algorithm? No, we got to reject it. Okay. Right, so that's the first. Then let's compare to PCA in terms of variance reduction, right? So in PCA, you extract this M dimension, and which are the eigenvectors of the covariance matrix sigma with these eigenvalues, right? And the bound residual variance, you use the largest eigenvalues of from m plus 1 to LD, right? Of the ones that you're not extracting. In GFR, which is our algorithm, the residual variance is bounded by epsilon, right? Used to threshold the variance at the jth step. Is it mine? No, the problem with St. Louis is that there are occasional tornadoes. Was it working? Huh? Was it working? No, there was a thing. My wife says, "Can you call me?" as well, but I guess she's still alive. I don't know. It was some alert. Actually, 2 weeks ago, the tornado blew through our neighborhood. We were one of the few houses without damages and without losing electricity. So hopefully it did not happen again. Anyway, so this is more important. Okay, so all right. So here, let me give you the results. So for identical epsilon, so that we compare, it's a fair comparison, right? Which is the threshold or remaining eigenvalue, right? You will see that GFR extracts much fewer direction than PCA, right? And this is up to an order of magnitude, right? So on the x-axis, you see the epsilon, right? Which is the remaining, it's a proxy to the remaining information that is left in the data, right? And when epsilon is equal, you will see that, right, the GFR, and here we compare GFR with different degrees of polynomial. Remember, you get to choose your family function. Of course, the richer the family function, the more information you can extract, right? And that's why you see that the one with polynomials of degree 4 achieves the better results, right? But here it's up to an order of magnitude, right? Basically, with much less features, we can extract the same information as PCA. Okay. So as I said, I'm just going to allude to, right? We have in our paper, and if you're interested, I'll point you to it. It's in the archive. It has been submitted actually to Transactions of Information Theory. Hopefully, it will be accepted there soon. This is the theoretical algorithm I was alluding to, right? And if you make this assumption of the data having these epsilon redundancies, which is something I don't want to really go into details, we can guarantee that the conditional entropy is actually 0. Right? The problem is that you cannot really apply. You don't really know whether the data that you have satisfies this condition. Okay. The other thing that you can do is, and I'm going to go quick, you can apply very quickly these algorithms to feature selection, right? Where basically what you do, instead of, you have to solve a different optimization problem, which is integer problem, because instead of finding the combination of the vectors, you have to select them, okay? But the structure, this iterative redundance removal, stays the same. Okay. All right. So up until now, we have developed a number of Gram-Schmidt algorithms for dimensionality reduction, where you fix a set of functions f, you project, orthogonalize, or subtract and repeat. Right. So this GFR applies to any reasonable distribution. It's a linear method, right? And you can see it as a probabilistic or nonlinear extension of PCA, right? And we showed that it's competitive against state-of-the-art linear methods and some nonlinear methods as well, right? And you provide guarantees, right? You provide guarantees, it performs well, it's simpler, and it's robust, as you can see, because you can have hyperparameters, right? And this GCA, which I did not get into, right? It's really the perfect feature extraction algorithm, but it is in an ideal setting, right? And both can be used for selection. Now, I want to give you an example of why I think this is important for explainability. Right. So we started working with a faculty in the medical school who works on genomics. They provide us with data, brain cell data set, right? And the goal would be to achieve biological interpretability of extracted features. Right? So we have a very sparse data set, right? We have a data set with over 53,000 features, but only 7,000 samples. It's a very tough problem, usually. And these are the problems that you usually encounter in genomics. And so what we did with two things. We applied PCA to the entire data set to extract 20 components. Right? For each of these 20 components, we selected the first 100 features, so the 100 features with the largest coefficients. Okay? And the second method is, instead of applying directly PCA to the data, we applied our feature selection to the data set to select a much lower number of features, like about 7,700 features. And then we applied PCA not on the entire data set, but on the selected features, right? And then we did the same thing. Selected feature, selected 100 features with the largest coefficients in each component. Okay? And then what we did, we performed gene ontology analysis on the selected features from steps 1 and 2. Basically, we looked at the feature extracted by the two methods, and we see whether these features are compatible with what we know about brain cells. Okay? And this is, so I'm going to show you a little bit the results. This is a map of the more important features, and this is just graphic. I don't pretend that you look into anything. It's just a graphic representation to see how the two methods provide very different importance in terms of features, right? They're drastically different, right? And just visually you'll see, right? I mean, the bigger the circle, the more important is the feature, is the feature, right? To a certain cell. Right, and we can notice also here, right? So on the left, you will see the method that we applied, right? By reducing first the number of features via selection and then applying PCA, versus the method number 1, which is applying to the entire data set. And so we ran it through our geneticist, who confirmed that some of the features, that all of the features extracted by our methods are relevant to brain data cells. While some of the features which were extracted by the methods that just applies PCA blindly reveals some features that are not expected gene ontology terms. They're nearly not relevant to brain cells, and this is known. This is prior information. Right? I hope this convinces you that methods of this sort can enhance interpretability. The last thing is, in terms of interpretability, which connects to to neural networks, is enhancing convolutional neural network interpretability. Right? There is this method called class activation mapping, which is a technique which is used to visualize region of an input image to which regions of an input image are the most important for a deep learning model's prediction. Right? So we applied, again, a method of similar, which we call GSF-CAM. So basically we use feature selection to select features from the features map to test to the last convolutional layer of a CNN. Right? And the residual variances of the selected features are calculated and then normalized to have unit norm. And then the normalized residual variances are used as the weight to generate the heat map, which gives you a map of the important features in an image. Right? First of all, analytically, right, we compared the method that we proposed to other CAM methods, right? And this average drop percentage, right? Don't ask me what it exactly means. What I know is that lower is better. And our method is the one that achieved the lowest average drop percentage. Actually, it's written here. The average decrease in the model's confidence when predictions are made using only the key regions of the input influence the original decision. Okay? And so this is what we did. You have a convolutional neural network. You apply to the last layer GFS. And then you generate your heat map, and then you overlay your heat map to the output, right? And this provides you with a graphical way of seeing what are the more important features, right? In this case, for recognition of the animal, right? And these are just some other experimental result, where we used ResNet XT50. Right? This is what you can do. Right? Okay. All right. So future work. Right. First of all, it's not really clear why we achieve similar performance to nonlinear methods, because in theory we should be doing worse. Right? So I think it is important these days to do more comparisons with deep learning methods in terms of robustness and the amount of data, and extend some of the results to other functional spaces. For instance, non-polynomial redundancy. Right here, we always use polynomial family functions, right? And also relationship to this tool called canonical correlation analysis. We'll also say that, given that our background is in systems and dynamics, I would love to look at possible application to model reduction, especially when it comes to PDEs, which of course contain naturally a lot of redundancy, which is given by the tight coupling that you have. Whether it could be applied to problems, I don't know, in fluid dynamics and the likes. And here are some references. The main paper is, you can find it here in the archive, and which is under review by, as I said, Transaction of Information Theory. I have to say that a lot of the stuff that we did, like this CAM comparison or the genomic analysis, is not in any paper yet because we haven't published it. All right, with this I will conclude, and I thank you for your attention. For online, not for.
Thanks for the presentation. So I have a question about your the example, the genomics example. So you said you have 50,000 plus feature and 7,000 samples. This means that you can't even train a neural network. Am I understanding correct?
I think it would be extremely difficult.
Yeah, well, so it's basically, that's why you didn't have any comparison, if I'm correct.
Yeah, people use PCA in this field still.
Okay,
still
so that's the dominant technique when it comes to this, at least this FIDO application.
At least our colleague who regularly publishes in Nature and surrogate journals, what he was previously using was PCA, and that's why he was so interested in the techniques that we've developed. Yeah.
Okay. Okay. I have other questions for that.
But go ahead.
Okay. So one argument in favor of using neural networks when it comes to classification of feature extractions is the flexibility. Now, how difficult is to define because I think it's up to you to define the vectors V1, V2, Vm, right? Mm-hmm. For a generic application. I mean, for instance, in the genomics example, I guess when you show the table, each of the end of the rows of the table was associated with a V, right, with a vector V.
Yes.
Then the question is a kind of systematic procedure to do this, to code, or you do it manually? I mean, that's...
Yeah, this is systematic. What is not systematic is... right. Yeah. To choose, for instance, how many features to extract. We extracted 7,000, but this could be an iterative process.
But isn't that given by what you're looking for? I mean, you want to extract a certain number of features. You know what you're looking for in the data, right? That's not user-defined in a way.
What do you mean? You don't know what you're looking for in the data. I mean, in this problem, this was just a demonstration, right? We had some prior knowledge. We wanted to test our algorithm against this prior knowledge. And that's why we cooked up this.
Okay.
This example, right? To see whether, right, in fact, the methods that we use are more explainable, right? And that was the reason for prefacing PCA with GFS. So in the hope that it would remove a lot of features that are irrelevant, so that PCA does not then...
That's basically the comparison we showed last, right?
That's right.
Well, the two steps.
Yeah.
Okay. Thank you.
So there was a question from Alessandro.
Thank you very much for the very nice talk. I was trying to understand what is different between this and the kernel PCA. Would you agree that the difference is that you do not project everything in the feature space, but here you just the deflation. So what you actually remove is a nonlinear contribution, but the components remain in the linear space.
Correct.
Okay.
That's the difference. Yeah.
That's the okay.
Yeah.
Okay. And then the other thing that I was thinking about was if you looked also into approaches such as nonlinear partially square, where or if you had, let's put it like this, if you had any problem where your state space or your x variables would be also related to would be the independent variables of some dependent variable. So if you have a relationship between your state space and some dependent variables.
So the assumption there is that was IID. The IID assumption was there. So if what you're saying was that non-IID, no,
yes.
we did not. Right?
Okay, yeah. Okay, because in that case you would also like to describe this relationship between the two spaces, right? So
but you don't have this information available usually when you have data, right?
Yes.
So that's why you assume it's IID. Example.
Yeah, but for the PD it could be interesting, because then in that case you might have...
I see what you're saying. Yeah.
You might have a source term in the PDE that is a function of the state.
Because so the problem there is that how do you encode the temporal coupling in this data? And you're correct. In that case, it wouldn't be IID, right? Because it's some kind of Markov structure.
Yeah.
Yes. Yeah.
Thank you. Anyway, it's exciting. Thanks.
Other questions? There is one on the back, and then okay, it's fine.
Oh, okay.
Please go for it.
Thanks. Thanks for interesting talk and for the interesting presentation. And I had a question concerning, that's more terminology one, but what did you mean by with, I think it was conditional entropy, am I correct?
Yes. Can we take it offline?
Oh, yeah, right. Yeah.
Yeah, it's right. The concept of entropy has to do with information theory. Basically relates to the informativeness of data, right? If you can predict the data, entropy is zero.
So it's like how much information
much uncertainty
remains useful.
Yeah, it remains useful. Yeah. After you remove, yes, correct.
And analogous to in thermodynamics, how much energy can still use, except that here it's with information.
So basically, what that is saying is that if the conditional entropy is zero, right, then the extracted data contains all the information. Everything else you can reconstruct from the extracted data, right? It's function of them. So in that sense, it contains no new information, right? If it's non-zero, then it means that you cannot reconstruct precisely the original data set from the extracted one, which means that you're leaving some information there. That's roughly at a high level what it means, right? And there's a mathematical, which you will learn in a couple of years.
So there was a question in the back.
Thank you so much for the talk. I don't know how stupid this question is going to be.
There are only stupid answers, no stupid questions.
Since you mentioned dynamical systems, I was very curious whether you could apply this to find projections in a simplex, for example, so that you can reduce your ODE to a specific subspace.
That's something that that I would like to look at. Yes, absolutely. That's one of the directions we were discussing before, right? Right. And as it was correctly pointed out, right? Then how do you deal with the this is one shot, right? Well, how do you deal with the temporal dependencies, right? Because that provides some information, right? So I don't know. We're starting to formulate that problem, to be honest with you, and the application would be more to PDEs. In PDEs, there's Stephen Brunton, for instance, University of Washington, who applies this Koopman operators, right, to fluid dynamics, right. So I think that's the flavor of the work. We want to see whether we could use some of these techniques into that methodology. Right.
Okay, thanks.
Okay, are there other questions? If not, or at least if you don't have questions that you want to make publicly, I want to thank once more Bruno for the nice talk.
Thank you.